Hello boys and girls. This is going to be a simple one. I am finally coming around implementing this very plain, straightforward gradient descent implementation that is also in a variant on the Wikipedia page. I'm going to use my virtual machine, the small wrapper for the while loop that I have introduced when I talked about computably enumerable sets. And I'm going to do it with just rational numbers. So given that floats are also rationals on a computer, this is basically a tautology. But my point being, I'm going to use the Python fractional class, and I'm just going to do the whole gradient descent only involving rational numbers. And when the rational numbers get too big of a denominator and numerators, then I will cut them down with the algorithm that we also implemented with the virtual machine 2 weeks ago, where you can, given any number, find another rational approximation, and that might be easier to handle because it has smaller numerators or denominators, and you can choose how big you want the representation to be, the approximation to be. And since the gradient descent involves taking the derivative, for that reason, basically, I made this video implementing taking the derivative of a polynomial, where I spoke of a polynomial in terms of an array of its coefficients. And the point of both of these is really to show that you can actually run the whole thing on a Turing machine. This is also discrete, and I built up all these individuals from scratch. I mean, I basically just used while statements and if statements at this point. This looks different than in when where is it here? When I implemented also a gradient descent for a particular problem when I talked about gradient descent for the deep neural networks. I also implemented the gradient descent algorithm there, but that was very much involved with the training data and very specific. This one in this video will also be specific because it's just this super small example from the Wikipedia page, but it will be more to the point. It will be less convoluted what happens. It will be very clear. And yeah, so if we quickly check out the Wikipedia page on the gradient descent, I would just say small words to repeat on how it works, right? The whole point of this is that you want to find the minimum of some function. It might have any dimension. In this picture, for example, you have like the levels of some well. This is basically some pit, and the gradient descent works by wherever you start, you check, taking the derivative, where is the gradient, where is the steepest way down, and for example, if you're here, then that would point in this general direction, and then you choose to go some amount of distance in this direction. And so you might end up here. The fact that this is a longer line than here means this is steeper here. But once you end up on here x1, then you take the derivative again, and it will show you again where is the steepest descent, and then you just follow that. The gradient descent in the AI example was, of course, a stochastic one, so there's some randomness mixed in particular. The training data was mixed up, and taking the derivative of basically of the error function in bunches, in different bunches of images. But that's a detail particular to the AI computer vision tasks. Here, this will all be completely deterministic. So when you run it twice, it will give the exact same results. And if you scroll, here's the explanation and a lot of infos, what can happen, what can go wrong. But eventually, if you scroll down, you get to a few implementations, and here's the Python implementation. This is really just what we are going to implement. So we have some function in this case. This will be with this function f of x is some polynomial to the fourth order. You have to take the derivative. This is how that works automatically is what this derivative video was about. But I mean, I suppose you remember the calculus rules. And then you have the derivative, and taking the steps means taking some guess at which you are at the moment, and some gamma here is the step size multiplying with this descent. So this is how far the next step will be. This is where the red arrows in the previous picture, and you subtract it from the current position. So if you look at this image again, here's the current position. We take the gradient. The gradient will actually show where it goes up, but we want to go down. That's why there's the minus sign. And this gamma or step size here also is just some number, and this is basically an art to choose which number to do there. It can also be chosen dynamically. Play around, but eventually this makes us go towards the minus sign, at least if we start in the correct interval, because as with many of these numerical algorithms, you can also have bad starting conditions and then things go wrong. But in this case, we have a tuned system. We will just do what Wikipedia does here with the same basically conditions, and it will work fine. But of course, it can go wrong if you have your parameters off, and this is the tedious tasks to find the right ones. So okay, so here we have this Wolfram alpha. I plotted this f of x. The function looks like that. When we want to find the minimum, means we will end up somewhere here. So this will be about 2.5. We can already see it in the image. What I will do, I will start, for example, here at 5, 6 or something, and then he will compute the slope. Will be like this. We choose some step size, and then he will naturally go there. And but if, for example, you have the step size high and he ends up on this side, then he will take the derivative again and want to walk in this direction. And so slowly we will converge by stepping more and more towards this well. But if, for example, in particular with this function, for example, here at 0, there's this 0 slope. So if you actually start there, then you will have 0 slope that makes a step size of 0. So you will actually never get out of there, because this is kind of this turning point. So you see the issues that can happen there. And then there's of course lots of tricks to get around these issues, but I will keep this video super short. Okay, so let's get to the coding part. I will only implement the actual update step and the halting step. I will make use of the virtual machine that I coded up in the previous videos already. You can take a quick look. I will not explain it much, except that it's really just a wrapper for a while loop, and it has a runner, and our only task is in this virtual machine approach to programming, to whatever algorithm we want to implement, to kind of squeeze it into a state and the state update so that the execution does what we want. So this is akin to a Turing machine, in that you have a bunch of steps that you take one after another, and it acts on some states. This is kind of the goal I want to achieve with this paradigm. And exactly with this virtual machine, the rational number approximation that I talked about, we had also implemented in this previous video. This was exactly this algorithm, and this really also runs with this virtual machine. But now we will use the virtual machine also for something else. And again, if I say virtual machine, I really just mean a wrapper for this while loop where we have to implement a halting condition and then update step. The halting condition will of course be when we're down in the well, but how do we detect whether we're down in the well? Well, our halting condition will be when he doesn't move anymore much. So when the difference between consecutive positions are very slow. So in particular when he ends up in the well, then he will have a flat situation. He will not be motivated to move anymore. He has found the minimum, hopefully, a minimum anyway, and therefore we define our halting condition to be not no change of the guess update, right? And for that sake, we have this precision at which point we consider movement to be no movement anymore. That's relevant for the accuracy that we want to achieve. And then, as I said, we have this step size, which is just some parameter that we choose that is just a multiplication factor of how far we actually want to jump per update step. We have this df. This is exactly the one that we have in this Wikipedia article as well. This is just the first derivative of this function that we want to find the minimum of. Literally just this function taking the derivative of 4 comes down and so on and so forth. We're going to implement the update step in these two functions, where update step will make use of this small function. We will implement the halting condition, and then this is how we also ran the other virtual machines, right? We set up a virtual machine with our update step and the halting condition. We initialize a state and then we run it, and then we'll print the result. And how this works here, we have the halting condition asking for how far did the guess move. So we have to take track of two guesses, the current guess of x and the previous guess, and we will compare them against each other. In fact, we might, and this is part of this dictionary in the state, we might actually take that as the first thing that we implement. So we take the state and we compute the delta by taking the guess minus the previous guess. So what is the previous guess? Guess, and then it should hold when the delta absolute value is smaller than the precision, right? So that's already our halting condition. Then how do we take a step? Well, the x comes in, the current guess comes in, and we do what what I motivated before. We take a step size step in the direction of the negative gradient. So that's that. It's also like very straightforward. And how does it look on the level of the update step? Well, we just have to take this step, and also in this update step I will also print some stuff. So what do we have? We unpack the state as we have it now, and then we save the last step. Like the current step becomes the previous step, and then we update the current step. So this becomes just this value g, and then we update the current state by setting it to this take step value, right? We do equals take step of g, but also, since I said, you know, I use this fractional class where I treat nothing as float but as actually as fraction of two numbers. I use this approximation that I had implemented 2 weeks ago and wrap it around just this typecast or just this approximation, so we stick with small fractions there. Okay, and let me also finish this printing statement. So we're going to print something and then we're going to sleep so that we actually see what's being printed, let's say for 0.4 seconds. And what do I want to print here? Well, I print what the current g is. I would actually also print it here as a float, just so you see the value better. And then also the delta that's currently being displayed. Okay, so dot format here. We have the state of g. Then we have float state of g, and then we have this difference again. Okay, and let's cast this to a float as well. And that should be pretty much it. Let me see. I usually have some bugs in there, so let's see how far we get. Okay. Let me run. Okay. Abs delta. Yeah, and it already works. So what happens here? My initial guess is 6, right? So my initial guess is somewhere here, like here 3, 4, 5, 6. So I'm there. He takes the first gradient. This will be a very sharp slope, and multiplies it by my step size constant, and jumps in this direction. So if you look at the output, let's go back to the start here. So he starts at 6. The previous value here is some random value, minus 9001, doesn't matter. So the first delta is huge. But then he makes the first update step, and the jump to the next updated point, you know, the step is a jump of minus 5.4. So he jumps to this fraction, which happens to be about 0.6. So he starts at 6 and then he jumps till there, right? And then he so this was a big jump. Then he takes another derivative, and first he jumped in a negative direction, and now he's here, and the slope is here going in this direction. So he will jump in the positive direction next, and that's what we see here. So in the next step, he jumps 0.02 in the positive direction. So he will be at 5. Let me calculate that in my head. 0.63, I guess. So 0.63. He's now slowly moving down the valley here, and that's what we see happening here. So these are these updates. They are all positives. He's slowly creeping in this direction, and here you see everything is always computed in terms of rationals. And he walks and walks and walks, and eventually the update step gets so small, they get to the order 10 to the minus 5, and he finds the final point about 2.249 something, and that ought to be the same thing that they also got out there. I mean, the commas might not be the exact same, because they might have a different precision and whatnot, but and different implementation, and not using the same approximation with the rationals, but it works in the same accuracy, let's say. Okay, we can also try, like if I start actually at -2, so my first guess being here, so he will only make positive steps presumably, right? Let's test it. See, it looks like he's moving super slowly. Yeah, this is too boring. Sorry. Let's try to find an interesting starting point there. If we started at 1, for example, I mean, we probably crossed that in the first trial. I can also, of course, grow the step size, right? So, okay. So we see that. What happens if we go up with the step size? Will be a little bit brutal, maybe 0.1 per step, but okay, let's see. We see we have some issue here. Now he like jumps back and forth. That's what you get. See, this is the issue. So he will probably not find the minimum here, because this is just this naive approach, and the parameters are nicely tuned. So you see how the hardship comes in here. I also want to show you, if I start at 0, where the slope is also 0, then he immediately like stops, because he already there's no slope to go. He doesn't make a big update step, and he thinks, oh, I'm good, and finds a minimum, even though it's the flat plateau. Okay, so that's how that works, and there are billion of variations of the algorithm and making it more robust and more fast and all these things, more efficient. But that's how gradient descent works in a nutshell. Take care.